In this video, Team Bubble will be talking about the carburetor of a lawnmower engine. The primary engine that is used in a lawnmower is the four-stroke engine. There are four stages of the four-stroke engine: intake, compression, power, and exhaust. The intake stroke first brings the air-fuel mixture into the combustion chamber through opening the intake valve, which then pushes the piston down. The compression stroke then brings the piston back up, compressing this mixture. Then, during the power stroke, the air-fuel mixture is ignited by the spark plug, causing an explosion and bringing the piston down. During the final stage, which is the exhaust stroke, the gases leave through the exhaust valve as the piston pushes it back up. Here is our initial opening of the lawnmower cover. In the upper center photo, we see the flywheel, which keeps the crankshaft turning, as shown in the video, by storing momentum from combustion and keeps the engine from overheating. In the picture in the upper right, we see the two rocker arms on a different side of the engine, which translates the movement of the camshaft to the up and down movement of the intake and exhaust valves.
Seen in the four-stroke engine, there's an air-fuel mixture that is brought into the combustion chamber during the intake stroke. The carburetor's role in this case is to create this air-fuel mixture before it goes into the chamber by mixing the fuel with the air stoichiometrically. The carburetor creates the air-fuel mixture by accelerating the oxidizing fluid, which decreases the pressure of the fluid and creates a pressure vacuum that draws in fuel. Components of the carburetor include the venturi that accelerates the fluid, a choke valve where air enters, a float chamber where fuel is held, and a throttle valve where the air-fuel mixture leaves. The equations used in analysis for carburetors are Bernoulli's equation, the conservation of mass equation, and the pressure force exerted on a control surface.
A key part of the carburetor is the venturi, which is a pipe with a section inside that is narrower in cross section. Similar to a rocket nozzle, the narrow part or the throat of the venturi will speed up the fluid that enters it, in this case air, and in doing so, it will lower the pressure. This lowered pressure will then suck up fuel from the reservoir below the venturi. There are two valves at each end of the venturi. The choke valve, which controls the amount of air that enters the venturi, and the throttle valve, which controls the amount of air-fuel mixture that exits the venturi to the intake manifold of the engine.
The term venturi is used to describe a tube whose cross-sectional area is reduced with the purpose of reducing the pressure. Since we assume that the flow from the wide cross-section is inviscid, then we also assume there is a large Reynolds number and a low Mach number. There are also viscous losses downstream of the throat. A key concept to note here is the conservation of mass, since the velocity of the throat must be higher than that in the wider regions of the tube, and also means that the velocity in the throat increases by the ratio of areas. Bernoulli's principle also applies here as the throat flow increases, so pressure must go down per the Bernoulli equation. The Venturi effect also is something to note here as well.
Assumptions made with our analysis include the incompressible flow approximation, where density is constant due to a Mach number of flow less than 0.3, and viscid flow, where losses due to viscous stresses are neglected due to a high Reynolds number flow, steady flow, where fluid properties do not vary with time, and quasi-one-dimensional flow, where fluid motion is approximated to be in one dimension.
By dissecting our lawnmower, we were able to measure critical values of the carburetor and take note of given engine parameters and atmospheric air values. The notes in blue were used to calculate the pressure at the venturi's throat. Using the Bernoulli equation, we can rearrange for this pressure at the throat in terms of the inlet pressure, which is atmospheric pressure, air density, and the speeds before and at the throat. To solve for the speed from the choke to the throat, we can use the volumetric flow rate derived from the engine's volumetric displacement, RPM, and the cross-sectional choke area that we approximated as a rectangle. Using the conservation of mass, we can solve for the velocity at the throat using the initial velocity we just solved for and known choke and throat areas. Plugging these values into a rearranged Bernoulli equation, we get a pressure of 99.6 kilopascals. This pressure and speed at the throat match the expectation that as throat flow increases, the pressure should decrease.